Tonicity is how tonic or how concentrated a solution or a cell is. It's fluid, okay? Solutions with lower solute concentration than the cells, we say those are hypotonic. Here comes some Latin. It means below the tonicity. The concentration of solute is lower than what's in the cell. In this situation, this ends up pulling water into the cell. The cell can have water molecules cross its lipid bilayer into the cell, and this could cause the cell to swell and lyse or burst, explode. Yes? Okay. Solutions with higher solute concentration than the cells that are within the solution, we call those solutions hypertonic. That means they have a tonicity or concentration that's greater than what's in the other solution or inside the cell. Those will pull water out of the cell, okay? And the cell could shrivel up and crenate, something we call crenation, where it cripples in sort of in on itself. It crenates and it shrivels up. Bad. Either one of these is bad, okay? Lysing is the worst because it's completely dead. There's no coming back from that. It exploded, it ruptured, that cell's out of commission. Particularly important when it comes to the blood cells. Solutions with the same solute concentration, so the same amount of salts, sugars, stuff in them, as the inside of the cells, we call those solutions isotonic, means same tonicity. This is where you want to be. In your body, in your blood, in your tissues, in your fluids, your body, we want to be isotonic, right? And if not, the cell is going to keep ways to keep things from moving and to stay where it's at. But in general, your blood plasma, the fluid of your blood, has to be sort of an isotonic situation. Otherwise, water's going to move in and out of your red blood cells. Okay, so no osmosis is going to occur here. Osmosis is occurring here. Osmosis is occurring here. In this case, they lyse and they swell. In this case, they shrivel and they crenate. Very bad, okay? So this comes into play when we talk about blood and transfusions and IVs. The solutions of those fluids have to be isotonic to your red blood cells. If they are not, they could damage and kill your red blood cells. And if your red blood cells all rupture and die, you don't survive. Yes? Make sense? Yes.
So the first one is saying like when there's like too much water that it gets bigger, and then the second one saying if there's not enough water.
It's not enough or too much. What it is if a solution has less stuff than the cells have, water is actually going to be drawn towards the stuff, and the stuff is inside the cells. It's going to make them swell. Water goes towards the stuff. So if there's more solutes in whatever area, that's where water is going to go to equilibrate and even out. So if you put it in a solution that has a higher solute concentration, water is going to go towards the stuff and it's going to exit the cell and make the cell shrivel in on itself. So you got to just think about this. Read this section in your textbook and think about this. It's just osmosis. Water is going from where it's high to where it's low, and again, water is going towards the stuff. Wherever the more stuff is, that's where the water is going to go. So in a hypertonic solution that's got more stuff, the water inside of the cell is actually going to leave. It's going to be like, I'm going out of here. If you put it in a hypotonic, not a lot of stuff in the surrounding solution, water's going to go from the outside towards the stuff or the cell that's inside of the cell. It's going to lyse and rupture. Yes? This is visually what it looks like.
The solution is just like what the cell is in.
Mm-hmm. Okay. Solution is just what the cell's in. So this is your blood plasma, what your cells are floating in, or this is an IV. If we give you an IV line or something, we transfuse new blood, or we transfuse in sugar water, or whatever. It's that solution makeup that's critical. So we can either, isotonic solution's got the same amount of stuff, concentration inside as outside. Osmosis is going to be net in both directions. There's no change in water inside of the cell. It's going to stay the same. You put in a hypotonic, less salt solution, water's going to go towards the stuff. It's going to come into the cell. This could potentially lyse and sort of bust and break because it gets too full, it swells. Ruptures the plasma membrane. You put in a solution that has too much salt, water's going to go from where it's high inside the cell to where the stuff is, and it's going to exit the cell. In this case, it crenates in, it envelopes in on itself, and what we call crenation, it kind of folds in and collapses on itself. Okay. Have you guys read this section of the book? Okay. If it still makes no sense, make sure you read those sections of the book. And just go over tonicity and hypertonic, and isotonic. It's basically just osmosis. But if you always remember, water goes towards the stuff. Wherever more of the stuff is, that is where water is going to go. Every single time, you can predict it. Okay, so that's why it's important. We have some other membrane transport mechanisms because a lot of things can't cross the cell. So they need some help. They need additional help. We've got transporters or carriers that will help get these other things across the cell. So facilitated diffusion is how we can get molecules down their gradient through a protein, through an integral protein. So diffusion in that it's still going from where it's a high concentration to where it's low, but it's facilitated in that it has to go through a carrier or a transporter, a protein in the membrane. We've got another type that gets stuff into the cell that wouldn't naturally be able to get in based on its chemistry. We've got active transport, and this is where integral proteins can actually move a molecule or type of molecule across the plasma membrane against its concentration gradient. Okay, so if I'm moving a molecule against its concentration gradient, I'm moving that molecule, or the cell is moving that molecule from actually low to high. In physics, in the world, like in the universe, that does not happen unless you put energy or work into that process, right? Diffusion is the natural movement of molecules and bouncing and equilibrating. If I'm going to pump a molecule or an ion or something against its gradient, I'm going to use an integral protein, and I've got to put energy into that process because I'm pumping it and building up a gradient. I'm pumping it from low to high instead of letting it just go from high to low. So this note takes ATP. This takes energy. You have to put ATP into that little carrier, this transporter, to actually pump that particular molecule against its gradient. And we'll look at sort of examples of these, and we'll see if we get these core principles. We've got lipid-soluble solids, little small little lipids, and it looks like they're just crossing right through the lipid bilayer, coming in the cell. What would you call that? We just talked about membrane transport: diffusion, osmosis, facilitated diffusion, and active transport. Right? Those four elements of membrane transport. What is happening here? Diffusion, right? This is simple diffusion going from high to low, simple diffusion. Water molecules are going from where there's more water molecules to where there's less. Osmosis. And they're using an aquaporin channel so they can go real fast, right? Now we got solids. I'm going to say these are ions. These are like sodium ions. They have a charge. We've got an integral protein with a pore, so it's a channel. It's an ion channel. These guys are going from where they're high to where they're low. What would we call this mechanism right here?
Active transport.
Facilitated diffusion. Diffusion, it's going from high to low. It's just using a facilitated ion channel or carrier to get it through. So facilitated diffusion. This one, this isn't a great representation. I'm going to add more to make it more dramatic. It should have. I'm getting this to go from where it's low to where it's high outside. So now it's going from low to high. I will even say that. It's low in here, it's high out there. It's using a transporter, and your cells have to burn ATP to operate this transporter because it's not going to go on its own. What would that be? Active transport. That one's active transport because you are actively pumping against the natural gradient. And anything active, muscle movement, pumping substances out of the cell, it requires ATP. So it actually is an active process that takes ATP. So simple diffusion, osmosis through aquaporins, facilitated diffusion, and active transport. Yes? Okay. There's some other membrane transport processes that are like bulk movements. They're not little water molecules going through or ion channels going through pores. They're actually taking in lots of particles or ejecting a lot of different particles, and that is endocytosis and exocytosis. This is how particles enter cells in like sort of mass movements. Phagocytosis is cell eating in Latin. So this is a cell taking in big amounts of particulate matter and food stuff. Pinocytosis is cell drinking, taking in big packets of fluid into the cell. Endo, coming into the cell. Exocytosis is the opposite. It's exiting the cell or leaving the cell. There is a type of receptor-mediated endocytosis, And this means that there's receptors on the membrane that when they get bound by a certain molecule, it triggers the cell to actually sort of invaginate in and pinch it and come into the cell. And they take it in because it's binding to specific receptors. So certain molecules, things like cholesterol, how cholesterol molecules, small little cholesterol molecules, how they can enter the cell happens through this receptor-mediated endocytosis. So there's a lot of cholesterol. The cells bind with their receptor, they bind to the cholesterol, and it triggers in taking in a whole bunch of that cholesterol right inside of the cell. All types of endocytosis. Exocytosis, that moves substances out of the cell. So it's ejecting materials out of the cell. And we'll look more at that later. Cell eating, so here's a bolus of food, nutrients you've taken in. You have cells, say, lining the gut. They're taking in boluses of food. In this case, they're taking in packets of water over here. This one, there's receptors in the plasma membrane waiting, and when there's a molecule that's high in concentration, like cholesterol molecules floating around, they will bind to the receptors and trigger this membrane to actually invaginate, pinch in, and go inside of the cell. So the cell can take in a whole bunch of that particular molecule. So what is this one? Cell eating. What do we call it?
Phagocytosis.
Phagocytosis. It's a type of endocytosis. Cell drinking. Water pinocytosis. And then binding to receptors and then coming into the cell. It's receptor-mediated endocytosis because it's binding to receptors and that triggers endocytosis. So these are the three major types: phagocytosis, pinocytosis, taking in water, lots of water, and then receptor-mediated. And notice this is cholesterol, uses cholesterol receptors in this way to take in lots of cholesterol inside your cells. We only have a couple minutes left. Yeah, I gotta stop there. So we're not gonna get through all the organelles, but I don't know if I should put them on this test or not.
No.
Okay, so we'll just stop. So the organelles and mitosis stem cells, they'll be on the next one. That'll be on the next one. And hopefully you already read that material. You can just review it and stuff later. We'll pick back up with this on Monday. So basically it's through, instead of through mitosis, it's through cells and transport mechanisms.
Okay.
So transport across cell membranes, where we sort of finish. That is, yeah? So they're transporting all the nutrients and water molecules and things that you need to get in and out, like fats, sugars, proteins, things you eat, and water. Yeah, different ways to get it in. So cholesterol binds to an active receptor, and it triggers it to the cell to take it in active quantities. Some other things like little ions or little sugars, bigger center ion channels or carriers. Yep, exactly. And so a lot of times bigger things will be taken in by endocytosis, and then smaller things, which are some things a lot of transporters like facilitate transporters. So the whole point is it's selective. It's like only when it needs certain things, it's taking those things in. When it wants to get rid of waste and stuff, it's getting rid of those different things. Yeah.
Wait, so is endocytosis going to be on the
Yeah, all the transport mechanism stuff. Yeah, all this. This is actually material that hopefully everybody already read in the book, and it's. Yes, I will take. No, keep it. I guess you're right. And Friday we have the test, so a lot of people already got it. It doesn't matter. You can give it to me Friday if you want, or you can give it to me now. It's up to you. And I'll write on it, but then I won't be able to give it to you. So. Actually, I give you a lab. I can give you smart and lab. Yeah. Yeah, where we end. So transport mechanisms, all the membranes are all here. So the organelles we didn't get into, unfortunately.